Okay, so in the introduction to sampling lecture, we had discussed the meaning of band-limited signals, and we had talked about how different real-world signals can be approximated as band-limited to certain frequencies, and then you can hopefully do sampling. So today we'll look at formally the relationship between the bandwidth of signals, continuous time signals, and the sampling frequency or the sampling time and we'll study that to ensure that two things happen. The first thing is, we had in the introduction to sampling lecture, we had talked about the concept of aliasing. So the question is, if you are given a band limited signal, what sampling frequency should you be using that there is no aliasing of high frequencies into lower ones? And the second thing that we'll study, which will be in a different lecture, will be once you take samples of your band limited signals, how do you do reconstruction of the original continuous time signal from its samples? So that's what we'll study, at least the first part of that in this lecture. And I just want to give you a sense of what does an ideal sampling look like. So in an ideal world, if you are given a continuous time signal, let's say GA of t, sampling can be represented by this expression, t equal to nt gn, which is simply saying that the way you sample is you have a continuous time signal coming in and you have a switch that closes every capital T seconds. So it closes, you get a new value of the signal, and you keep on doing that. So your samples are just whatever was the signal value at different multiples of the sampling period t. In a block diagram, people write that in different fashions. You will see pictures like the block will be written as C/D, which means continuous to discrete, which is effectively this above operation that I have shown you. Sometimes the block will and one of the things that this block has input is the capital T, the sampling period that you are using to sample your signal. Okay. Sometimes people will just call that a sampling block, so they will say sampler. Again, there will be an input capital T to the block, and you generate the sequence. Now, this is the mathematical description. In hardware, the devices that are used are called analog to digital converters. Or ADCs. And when you try to look at commercial ADCs, you will find terms like this is a 1 megahertz ADC. What 1 megahertz basically means is that the sampling frequency of that chip which is effectively doing this operation of closing the switch every t seconds, that frequency is 1 megahertz, for example. So a 1 megahertz ADC, it means that the sampling frequency is 10 to the 6 hertz, or t is 10 to the minus 6 seconds. And of course, ADCs have another parameter, which is the number of bits that it uses, which we'll study later. So the question we are interested in asking is, when does Gn preserve information in the continuous time signal Ga of t? Let's say you are given a 1 megahertz ADC, and you use that to sample a continuous time signal. When will that ADC preserve all the information in your continuous time signal? Okay. And that is equivalent to, so we have now understood the Fourier transform of both continuous time and discrete time signals. So we can, instead of asking the question about when does the time domain signal preserve information in the continuous time domain signal, we can also ask the same question in frequency domain, which is, when does, so the Fourier transform of your signal, discrete time signal, which is g of e to the j omega, preserves information in the original Fourier transform, which is Ga of j capital omega. Okay. So to look at this question, the first assumption we'll make is, right now just say that the input signal Ga of t is finite energy, which implies that Ga of j omega exists. So you have the usual Fourier transform formula. So this exists, and we are interested in asking if g of n is given by Ga of nt. So this is the sampling operation. This is your definition of the discrete time signal. Then when does the Fourier transform of that sequence, which is given by n equal to minus infinity to infinity, g of n e to the minus j omega n, contains information about the continuous time Fourier transform. Okay. Now, looking at it this way, it's a little difficult to be able to relate the Fourier transform of your discrete signal to the Fourier transform of your continuous signal. So what we'll do is divide our operation, which is in physical world, the operation of sampling is simply one switch closing again and again. We'll divide that operation into a couple of mathematical operations, which are there just to help us understand or do the analysis of the sampling operation. So the first operation we'll do is, instead of saying, so instead of looking at this sampling operation, which says that you simply sample your signal by closing the switch every t seconds, we'll first look at the following operation. So we say we are given this continuous time signal, and we multiply it with another continuous time signal p of t to generate gp of t. So we are going to divide our continuous to discrete operation into two operations, and the first operation is continuous to continuous operation. So what is this p of t? This p of t is a collection of impulses separated every t seconds. So this is called a periodic impulse stream of period capital T. So if you are interested in sampling every t seconds, then the first operation is we multiply our signal with an impulse train where each impulse is separated by capital T seconds. And at the output, we get this GP of T, which I'll be referring to as impulse sampled signal. This is still a continuous time signal. So what is the expression of GP of T? I'll just plug in GP of T is GA of T times PT. I plug in the value of PT. Delta of T minus NT. Then I take GA of T inside the summation. So that's GA of T, delta of T minus NT. Now here we use the shifting property of the direct delta. So using the shifting property, which is just reminding again that if you multiply a function with a shifted impulse, then what you get is that function evaluated at the location of the impulse times the impulse. Right? So using that same shifting property, we can write GA evaluated at NT delta of T minus NT. But this GA of NT is exactly what we had defined our discrete time sequence. Our discrete time sequence is defined in terms of GA of T evaluated at multiples of T. Right? So what we get, I can replace that by Gn, and so I get n from minus infinity to infinity, G of n delta of T minus NT. Okay, so note that GP of T, this impulse sample signal, is a continuous time signal. But now you can start seeing the relationship between the continuous time signal, the impulse sample signal, and the discrete time samples that you will be getting. This whole stuff that we have done is only for mathematical convenience, because it helps us link the continuous time signal to the discrete time signal. Okay. So here is a graphical representation of what we were talking about. We said we have a continuous time signal, and you multiply it with a impulse train PT to get this impulse sample signal GP of T. Now this is what the impulse train looks like. Whatever is the time duration you are interested in, you are saying I'll generate an impulse train where you have infinite number of impulses separated by period t, and then you are multiplying that with GA of T. So this is your GA of T, and you are now doing multiplication of this impulse train with this signal. And what happens at the end is that GP of t is nothing but an impulse train again, which is simply the impulse train is still located at nt periods, but now the area of those impulses will be modulated, will be multiplied by whatever was the signal value at that location. So this is what you get at the end of the day. This is these impulses whose area is proportional to whatever was the signal value. Right? So here, your area is proportional to the signal value here. These are the values that you get. And these are indeed also the samples that you were going to get in the discrete time setting. So this is what GP of t looks like. A bunch of impulses separated by time periods t, but their area now modulated by whatever was the signal value at that point. Now the question is, how do you recover Gn, the discrete time sequence, from your impulse sample signal? So how to go from Gp of t to Gn? Well, that is simple, because Gp of t, this is your Gp of t, it's simply a collection of impulses, and you can just read the area of each impulse to figure out what is the Gn value. So that operation mathematically is very simple. You have the impulse sample signal, and you say impulse train to sequence conversion is simply you read the values of the area of each impulses. Again, not a physical operation, but going from the impulse sample signal to the discrete time signal, it's trivial. You are given a bunch of impulses, you just read their areas. Okay? So mathematically, the operation that we were interested in, which is this operation, we are breaking that operation down into two pieces. One piece is multiplication with this periodic impulse train to get Gp of t, and the other operation is read area of impulses, because whatever is the area of impulses is your discrete time sequence. So you just read the area of the impulses to get Gn. Now you have effectively broken down your sampling operation into two pieces. And if you are interested in asking when is there no loss of information in going from the continuous time signal to the discrete time signal, you can ask yourself, when is there no loss in going from this Ga of t to Gp of t, and then when is there no loss in going from Gp of t to the sequence Gn? Okay. Now, going from Gp of t to G of n actually incurs no loss of information. All you are doing is read the areas of the impulses, and if you want to reconstruct that train of impulses, you put back that area and you get back the signal that you are interested in. Right? So if someone says construct from Gn Gp of t, all you have to do is create an impulse train The period of that impulse train is t with area equal to Gn. So Gp of t, you can construct that again simply by going from the sequence to the impulse train. So this second block entails no loss of information. So what we are really interested in is then when you are taking your continuous time signal, you multiply it with the periodic impulse train to get this impulse sample signal, which is now only consisting of impulses. All the values in between are gone. When is there no loss of information in that case? So that will be our focus. To understand the sampling theorem, we'll be interested in figuring out when does going from GA of t to GP of t till no loss of information. And again, instead of looking at the time domain, we can ask that same question in the frequency domain. So an equivalent question is, does GP of j omega, which is the Fourier transform of GP of t, contain all the information about GA of j omega, which is the Fourier transform of your original signal? Okay. So to look at that, we have to again just remind ourselves the definition. GP of t is GA of t times P of t. So now I'm interested in the Fourier transform of the impulse sample signal. That means I'm interested in the Fourier transform of GA of t and P of t. The Fourier transform of the multiplication of these two sequences will be, there will be a 1 over 2 pi factor because the units we are using are radians per second times the Fourier transform of GA of t convolved with the Fourier transform of P of t. So that is 1 over 2 pi. Let's call that GA of j omega. And let's call the Fourier transform of P of t as P of j omega. Convolved with P of j omega. So now we have to understand then GA of j omega is whatever it is. We are interested in understanding what is Pj of omega, which is the Fourier transform of P of t. So the three facts we have talked about are that number one, we cannot use the continuous time Fourier transform formula directly, since P of t has infinite energy. But P of t is periodic with period t. So this means that it has a Fourier series representation. So what is the Fourier series? I'll work with the expression using the complex sinusoids. So it's given by k from minus infinity to infinity, c of k e to the j 2 pi kt over capital T, where k goes from 0 plus minus 1 and so forth. or sometimes we'll write that as k from minus infinity to infinity, ck e to the j k omega capital T times little t, where omega capital T is defined as 2 pi over t. Yeah. So the only thing we need to describe the Fourier series are the Fourier series coefficients. And how do we compute the Fourier series coefficients? We just take minus 1 over t, we take the average, minus t by 2 to t by 2, any period. I'm working with t by 2 to minus t by 2 to t by 2. I'm not interested in using from 0 to t because of the edge effects, because you have an impulse at 0 and you have an impulse at t, which can make it difficult. So we are trying to go from minus t by 2 to t by 2. So that's p of t e to the minus jk omega t t dt. Now, between minus t by 2 and t by 2, there is only one impulse. It's a periodic impulse, but between minus t by 2 and t by 2, there is only one impulse. So that's 1 over t minus t by 2 to t by 2 delta of t e to the minus jk omega t t dt. And that will be simply use the shifting property, and then you're left with simply the area of the impulse, which is 1, so you get 1 over t. So this means that I can write my periodic impulse train as 1 over t summation k from minus infinity to infinity e to the j k omega capital T little t. So I have now written my impulse train as an infinite summation of complex sinusoids. Now I'll just do the Fourier transform of P of t, which is the Fourier transform of 1 over t summation e to the j k omega t little t, and using the linearity property of the Fourier transform, I get Fourier transform of simply e to the j k omega capital T little t. The Fourier transform of this complex sinusoid is simply an impulse at omega equal to capital omega t. So what you get is that you have 1 over t, and the area of this impulse is 2 pi. Okay? So what you get is 1 over t summation k from minus infinity to infinity, 2 pi, which is the area of the impulse, delta of omega minus k omega t. K omega equal to k omega t, because the frequency of this impulse is k omega t, which is equal to 2 pi over t summation k from minus infinity to infinity delta of omega minus k omega t. That's p of j omega. If you actually compare the form of p of t and its Fourier transform, you see a remarkable similarity. The Fourier transform of your periodic impulse train is also a collection of impulses separated by omega t in the frequency domain. So the Fourier transform of an impulse train with period capital T is also an impulse train with period omega t equal to 2 pi over t, and area of impulses equal to 2 pi over t. Yeah. So the Fourier transform of your periodic impulse train looks like this. This is 0, omega t, minus omega t, and so forth. And the area of each of these impulses is 2 pi over t. So now we can go back to our expression that we had started with. We were interested in computing the Fourier transform of our periodic, our impulse sample signal, and we had written that as the convolution of our original signal with the Fourier transform of the periodic impulse train. We have now computed this P of j omega. So we can go back to this expression, plug the value of P of j omega, and try to figure out what does the Fourier transform look like. So we had Gp of j omega equals to 1 over 2 pi Ga of j omega convolution with P of j omega. But P of j omega we just computed. That's 2 pi over t, k minus infinity to infinity delta of omega minus k omega t. Now, convolution is linear, so I'll just do that linear operation. I'll get 2 pi over 2 pi times t, summation k from minus infinity to infinity Ga of j omega, convolution with delta of omega minus k omega t. Now here again we want to use a property of impulses. You are convolving a signal with an impulse. It doesn't matter whether the impulse is in time domain or frequency domain. A reminder of the convolution property of an impulse. If you convolve a signal, a function with an impulse which is shifted at x naught, then you get back the same function but only shifted at x naught. So if I use that, now my variables, instead of x and x naught, my variables are capital omega and k omega t. But the same property holds. I will get back Ga. Remember, J is not a variable. J is just there to remind you that it's complex valued. So my variable is omega minus k omega t. So I cancel this. I get back 1 over t summation k from minus infinity to infinity Ga of j omega minus k omega t. So this is one of the most important relationships that you should remember when it comes to the sampling expression. We'll be referring to this again and again in future lectures. So what is this expression saying? Let's try to parse that. We said that you take your continuous time signal, you multiply it with a periodic impulse train of period t, and you get back Gp of t. And if you compute the Fourier transform of that Gp of t, this is what it looks like. It's So the Fourier transform of this impulse sampled signal is related to the Fourier transform of the original signal according to this relationship. And this relationship has three properties that you should always try to intuitively remember. The first property is you look at this, and if I look at the summation, you have this summation of GA, different copies of your original Fourier transform, shifted but different copies. So the first thing that happens is that the continuous time Fourier transform of GA of J omega gets converted into multiple copies. What do I mean by multiple copies? That's given by the summation expression. And the second is that each copy of your Fourier transform is scaled by, so you have this 1 over t factor, is scaled by 1 over t. So A, you get multiple copies. B, you have scaling of the Fourier transform. And C, the multiple copies that you get are shifted in the frequency domain. Okay? Each copy is shifted by a multiple of your sampling frequency, k omega t equals to k times 2 pi over t. So it's shifted according to whatever the sampling frequency you have. We'll look at this expression also then graphically to help us understand the physical meaning of this. So here is a pictorial understanding of what is happening in frequency domain when you do the time domain operation of multiplication of GA of t with an impulse train. Let's assume that this is just an example. The Fourier transform of this GA of t, let's assume that it looks like this. It's band limited to omega m radians per second. The previous expression that we wrote, by the way, holds regardless of whether the signal is band limited or not. Okay? Now, let's take this particular example. This is what the Fourier transform, let's say, look like. And we said that the Fourier transform of GP then looks like 1 over t summation of k GA of j omega minus k omega t. So how we derived that is that we were looking at convolution of this with the convolution of the Fourier transform of our impulse train. And the impulse train's Fourier transform was 2 pi over t and since 2 pi's get cancelled, let's make it 1 over t. So you are convolving this with this periodic impulse train, and what happens is you get multiple copies. Now you get your original Fourier transform shifted at the locations of these impulses. So at the end of the day, what happens is you have the same Fourier transform at 0 frequency, of course, but also a copy of that at omega t frequency, at minus omega t frequency, 2 omega t, 3 omega t, and so forth. So this is what I meant by, first of all, you get multiple copies. Initially, you started with this one copy in the middle. Now you have multiple copies. and the multiple copies are shifted at multiples of your sampling frequency. And the total Fourier transform is scaled by 1 over t. So each of the copies is scaled by 1 over t. Okay. So this is what this expression translates into if you had known the shape of the Fourier transform of your original signal. So we had started with the question of when does the impulse sample signal does not lose information. We had gone on this track because we were interested in answering that question. And now we can ask that when does GP of j omega contain all information about GA of j omega. Okay. If that's the case, then we say that we have no loss of information in that first block of the sampling. And then the second block, of course, is we have already argued that it never loses any information. So one of the ways to not lose information, if I just look at it graphically in this picture, we'll show that mathematically later too, but if I just look at graphically, this is my original Fourier transform. And if I can find this Fourier transform in the Fourier transform of my impulse sample signal, if I can see that Fourier transform, then that means I'm not losing any information. Now, to do that, what I must make sure is that the multiple copies of the Fourier transform that I'm getting, they don't overlap on each other. So what are the conditions for the overlap not to happen? This point is omega t, and this is the second copy, right? So this is GA of j omega minus omega t. And we must make sure that this leftmost point of that does not cross over this omega m point. So the first condition that we need to make sure is that this leftmost point, which is omega t minus omega m, that remains above omega m. And that will hold for all different copies also. So this will imply that omega t has to be bigger than 2 omega m. Okay. I can ask a similar question about this copy and this point, and I'll end up with the same expression. So what is this? This point is minus omega t plus omega m. Right? So if I focus on this copy, I can see that I don't want this point to cross over into this copy. So the condition there will be that minus omega t plus omega m is less than or equal to omega m. Once again, if I solve that, I get the same condition. Omega t is greater than or equal to 2 omega m. You can focus on any other copy and you'll get the same conclusion. So minus omega m. So in all cases, the expression that you get is the condition to not lose any information is that omega t is greater than or equal to 2 omega m, which is called that the sampling frequency is at least twice the bandwidth. or twice the maximum frequency present in GA of t. If the maximum frequency present in GA of t is not symmetric in the positive and negative side, then this expression will have to change a little bit. Right? Okay, so this condition is that if your signal changes faster, then you better measure your signal, sample your signal more often. That's what this condition means. Now, the question is, this is sort of a sufficient condition, but is it true that if omega t is less than 2 omega m, then we lose information? So for that, let's look at the case when that condition happens. Okay. And what will happen is now that the second copy will overlap with the first copy, and you have the addition operation. And the third copy will overlap with the second copy, and so forth. So once you do the addition operation, this is what GP of j omega look like. Now, the trouble is, once I take away the Fourier transform of GA of t, you cannot tell whether this picture came because your input signal looked like this, okay, or your input signal looked like this. Because both of them, when you add up, they give you the same Fourier transform expression. So that is sort of a way to convince you that if indeed you don't verify that condition, then you cannot distinguish between different signals that could have generated that Fourier transform. So you can no longer see the original Fourier transform in your Fourier transform of this impulse sample signal. Okay, so all the analysis that we did, it basically took us to the main condition that we derived, that to make sure there is no loss of information, you better sample your signal at twice the maximum frequency in your signal. And that is what's known as the Shannon-Nyquist or the Shannon-Nyquist-Kotelnikov, based upon which people contributed to this theorem. So we'll just call it the sampling theorem for band-limited signals. And that's the crux of the lecture. All the analysis that we did is basically saying that we first make the assumption that GA of t is a band-limited signal such that GA of j omega is 0 for all omega greater than omega m radians per second. So omega m is some value. So if this is the condition, then GA of t can be uniquely reconstructed from its samples G of n equal to GA of nt. So you evaluate your signal at multiples of t as long as the following condition is satisfied. 2 pi over t, which is called the sampling frequency, omega t, you sometimes call it omega s also, that is greater than or equal to 2 times the bandwidth, 2 omega m. This condition is called the Nyquist criterion. You can look, so this is a version where you are told that the signal is band limited to omega m radians per second, and you say I must sample it at twice the frequency. Sometimes the sampling frequency is fixed, and you can look at it the other way too. So another variant of this could be that if omega t is the sampling frequency, then the input signal must not have any frequency above omega t over 2, which is the same condition as above but stated now differently. So omega t over 2, the maximum frequency, if I give you an ADC whose sampling frequency is fixed, then you know that that ADC cannot handle certain frequencies. If it's a 1 megahertz or if it's a 2 megahertz ADC, then it cannot handle frequencies above 1 megahertz. Okay? If you do that, then you will lose information. So this omega t by 2, the maximum frequency that a sampling system can handle, that's called Nyquist frequency or folding frequency, and we'll see why it's called folding frequency later, or cutoff frequency. Okay. And the frequency 2 omega m is called Nyquist rate. The general terms that are used in sampling theory are if omega t is bigger than 2 omega m, then we say that we are oversampling. And in pretty much all DSP systems, you oversample because nothing in the world is perfectly band limited. So because of that, you try to oversample. If omega t is exactly equal to 2 omega m, then we say it's critical sampling. And if omega t is less than 2 omega m, then we say that we are undersampling. So the example in music is we consider music to be band limited to approximately 20 kilohertz, and the standard of sampling, so CD quality sampling, is, so CD quality sampling is 44.1 kilohertz, which, as if you look at the description, it falls under the oversampling region. The 4.1 kilohertz margin is there to take care of imperfect filters and all the other implementation details. Okay. Similarly, in telephony, the assumption you band limited the voice to typically 3.4 kilohertz, and the sampling takes place at 8 kilohertz. So you never actually sample at twice. You always give yourself some margin because of the imperfections in filtering and all those other operations. So just to reiterate, you are given two cases. One is you can say, I am given this signal, I know its approximate bandwidth, what's the sampling rate that I should use? What ADC should I use? Right? If you are trying to record someone's speech, you better have an ADC at least 8 kilohertz that samples at 8 kilohertz. Or someone could give you an ADC and say, this is the sampling frequency of this ADC. And you must make sure that the signal that goes into that ADC is no more than half of the sampling frequency of that ADC. Okay. This is just looking at when you does not lose any information. We'll have to look at how do you now reconstruct the signal from your samples. And that will be the subject of future lectures.